Hello everyone, my name is Om and today I'll be presenting our paper, A Study of Persistent Memory Bugs in the Linux Kernel. This is a joint work with Duo Zhang, Wei Zhu and my advisor Dr. Mai Zheng. Persistent memory devices are available right now. For example, Intel Optane DC persistent memory offers low latency and byte addressable access. This new storage technology has inspired many PM optimizations, such as new PM-aware file systems, paging techniques, PM indexes, and PM libraries. However, building correct PM-based systems is hard. Firstly, PM-related instructions must be used carefully. For example, to persist data A and B, we need to use CPU flush instructions such as CLWB. And to ensure ordering, we need to use memory fence instructions such as sfence. Moreover, it requires strong support from the kernel. Figure here shows the traditional stack on the left and the storage stack for PM devices on the right. We can observe that multiple subsystems including NVIDIA drivers, file systems, and memory management are being revised aggressively for PM. Such complexity may introduce obscure bugs that cause system crash, data corruption, and so on. Addressing the challenge requires cohesive effort from multiple directions, such as PM bug detection, PM programming support, and clear PM specifications, to name a few. All these directions will benefit from a better understanding of real-world PM-related bug characteristics. Many studies have been conducted to understand and guide the improvement of software. For example, Liu et al. Studied 100+ concurrency bugs in user-level programs and provide insights for concurrency bug detection. Another group of researchers studied more than 5,000 patches in traditional file systems and classified bugs into various patterns. More recently, Neil et al. Studied 60+ PM bugs in applications and designed 2 generic bug detection oracles. Yang et al. Studied the performance of PM software stack on an NVIDIA device. While these existing efforts have generated valuable insights, they do not cover the potential PM-related issues in the Linux kernel. We address this problem in this study. Going forward, I'll present our methodology followed by dataset analysis and the lessons learned. Typically, changes to the kernel are submitted in patches. We collect around 693,000 patches submitted to the Linux kernel source tree between 2011 and 2020. We then prune this dataset by searching for patches with PM-related keywords such as DAX, PMM, and others. This resulted in 2,541 patches. Next, we do a manual inspection of these patches to remove any noise. At the end, we had 1,350 PM-related patches. For these 1,300+ PM patches, we study each of them in depth. A patch typically consists of a patch header, patch description, and code changes. We read through them carefully to understand the purpose and logic. Moreover, we refer to relevant source code and documentation to better understand the dataset. From this dataset analysis, we would like to answer 3 sets of questions. First, what are the purpose of PM-related patches and how many are related to fixing correctness issues? Second, what type of PM-related bugs exist in the kernel and how are they fixed? Third, what are the limitations of existing PM bug detectors and what are the opportunities? Our study has few limitations. First, our dataset was refined using keyword search and manual examination, which may be incomplete. Second, we only study the bugs that were reported and fixed in mainline Linux kernel. There is a possibility that the kernel may contain other unknown trickier bugs. We believe that our study is one important step towards addressing the challenge. We first classify all patches into 3 categories. First, the dominant category of patches are related to feature. These include adding new PM feature and improving efficiency. Feature patches contribute to about 40% of our dataset. Interestingly, we find that more than 40 feature patches are proactive. That is, they were added to support PM features in the near future. For example, the developers extend existing flags to bit flags so as to support additional DAX flags. The second category is maintenance. These patches fix compilation issues and remove obsolete code. Maintenance patches contribute to 37% of our dataset. The third category of PM patches are bug fixes. These fix correctness issues such as misalignment of PM regions, data race issues, and others. Bug patches contribute to 23% of our dataset. We will look into this important category further. To sum up, we observe that overall, the patches can be classified into feature, maintenance, and bugs. Within this dataset, 23% are related to fixing correctness issues. Next, we look into bug characteristics. First, we identify where are the bugs in the Linux kernel. This figure shows the distribution of PM bug patches in the Linux kernel source tree. For simplicity, we only show the top-level directories in the kernel on the x-axis. The y-axis shows the number of PM bugs reported. We can see that PM bug patches involve many major kernel subsystems. This implies that we cannot only focus on one subsystem for PM bug detection. Next, we observe that drivers, file systems, and memory management subsystems contribute to about 74% of PM bugs. We find that in driver subsystems, most of the bugs are related to the introduction of new NVDIM drivers. This is consistent with previous studies that mention driver bugs are dominant in the kernel. In file systems, most bugs are related to the introduction of DAX support. Similarly, in memory management subsystem, most bugs are related to DAX page management. We also count the occurrence of individual files involved in the bug patches. The table here shows the top 10 most buggy files based on their occurrence. This verifies that adding DAX and NVDIM support are two major sources of introducing PM bugs in the kernel. To build robust PM systems, it is important to understand the types of bugs occurred. We find that PM bugs can be broadly classified into 5 types, namely hardware-dependent, semantic, concurrency, memory, and error code. First, we observe that many classic bug patterns are common. For example, there are semantic bugs caused by improper design, concurrency bugs caused by mismanagement of PM access, memory bugs caused by mismanagement of PM or DRAM components, and error code bugs due to improper handling of error codes. However, the root causes are often different from the bugs in traditional systems, and we will show some examples shortly. Besides the classic bug patterns, we observe that about 20% of bugs depend on PM device. We further classify hardware-dependent bugs into 4 subtypes. Specification bugs occur due to misunderstanding device or interface specifications. These are the most common hardware-dependent bugs observed. Alignment bugs occur due to mismatch between abstractions of PM device. Device or architecture incompatibility causes compatibility issues, and cache bugs occur due to misuse of cache-related operations. Misusing cache-related instructions has been the focus of many existing PM bug detection bugs. But we find that this issue is not as common as other subtypes in our dataset. Overall, hardware-dependent bugs may cause severe consequences such as missing or inaccessible PM device. To better understand these bugs, we provide a few examples. Here, a specification bug is caused due to the ambiguity in ACPI specification regarding if status of address range scrubbing is included in the output field. To validate this, the source code was supposed to remove 4 bytes from outfield. Instead, 8 bytes were removed. This caused a memory corruption. The bug was fixed by swapping values 8 and 4. Here is an example of alignment bug. The issue occurs due to misalignment between page frame number device and NVDIM namespace. While validating the PFN device alignment, the method does not take into account of the padding at the beginning of the namespace. This inconsistency makes the device inaccessible. In our study, we identify many issues related to concurrency. In particular, we observe that data race bugs involving DAX I/O are dominant. Here we show an example of data race bugs that occur due to the conflict between a write system call and DAX page fault handler. Here, thread 1 is attempting to read new data to DAX page, and thread 2 is attempting to read from the same page. The write system call invokes DAX IO map read write, which first allocates blocks for writes. After the write, the routine invalidates pages before updating the block mappings. But due to lack of proper locking, thread 2 may grab this mapping before it is updated. As a result, 0 pages are added to the radix tree and mapped to the page tables. This inconsistency is fixed by locking the exception entry before mapping the blocks. To quantitatively measure the complexity of fixing PM bugs, we first look into the bug patch size. Here we define bug patch size as the lines of code inserted and deleted. This figure shows the size distribution of PM bug patches. The x-axis shows the bug patch size and the y-axis shows the percentage of bug patches. We observe that 50% of PM bugs are fixed with less than 50 lines of code inserted and deleted. In contrast to FS bug patches, PM bugs tend to be larger. Second, we measure the patch scope. We define patch scope as the count of files or directories involved in the patch. The tables here show the percentage of patches involving different counts of files and directories. For simplicity, we only count the top-level directories in the Linux kernel source tree. In our dataset, 36% of patches modify more than one file, and about 7% patches modify 5 or more files. In addition, around 21% of patches involve fixes in multiple subsystems. This shows that fixing PM bugs involves fixing multiple files or multiple folders, which implies the complexity of PM bugs fix. In addition, it also implies that focus only on one subsystem for bug detection is not sufficient. We now look at if any bug fix strategies were employed. We find that bug fix strategies vary a lot depending on specific bug types. However, a common strategy used across various bug types is refining sanity checks. To understand this, we provide a few examples. Here, an incorrect sanity check was causing an infinite loop call. The method generic fsdax supported checks if the device supports direct access. This is done by checking daxdev variable and calling bdev dax supported in line 3. But this method calls dax supported, which in turn calls the same method. This results in an infinite loop call and the system gets stuck. Another example of sanity check is fixing an alignment issue. Here, the PFN device alignment validation fails due to the inaccurate check, which makes the device inaccessible. The inaccurate check is replaced with a call to isAlign method that accurately checks offset with recorded device alignment. In a few cases, we observe that kernel developers temporarily fix a bug by disabling a PM feature. For example, handling huge pages for DAX is disabled by making this feature depend on config broken. Developers also mention that such issues require larger rework. This further implies the complexity of PM bug fix. In summary, we observe that PM-related bugs can be broadly classified into 5 types. For bug fixes, developers employ diverse strategies and sanity checks are important. We then move on to the next section, that is implications on bug detection. Multiple PM bug detection tools have been proposed recently. We inspect 3 existing PM bug detectors to verify their effectiveness. The first one is PM test, which is one of the first PM-specific bug detectors. It identifies crash consistency bugs in both user and kernel space. But this tool relies on manual annotation of source code, which is not scalable for the Linux kernel. The second one is except detector, which is a follow-up work of PM test. It identifies inconsistency in pre- and post-failure execution of an application. Since except detector relies on Intel pin to record PM accesses, it cannot be easily extended to the kernel. Finally, Agamotto is a recent work that uses symbolic execution engine to identify durability issues in PM applications. Although it is possible to integrate this work with VMs to enable full-stack symbolic execution, novel PM-specific path reduction algorithms may be necessary to test the kernel. Besides PM bug detectors, great efforts have been made to detect non-PM bugs in the kernel. Especially, fuzzing-based tools are gaining significant traction recently. They have been effective at detecting bugs in the kernel. For example, Hydra identifies semantic bugs in traditional file systems. Razor and K-Race are 2 recent works that detect data race issues in the kernel. We observe that all of these tools require a virtualized or simplified environment to work. For example, Hydra relies on Linux kernel library to execute kernel code. Razor and K-Race employ QEMU to run the target kernel. Therefore, we believe that there is a general challenge and opportunity here. That is, many non-PM bug detectors may be extended to detect PM bugs in the kernel if we could emulate PM devices and interfaces precisely in virtualized or simplified environment. This brings us to the lessons we have learned in this study. Firstly, we observe that existing PM bug detectors only cover the tip of an iceberg. On the other hand, non-PM bug detectors have the potential to cover many bugs in our dataset with additional innovation. We also find that PM bug detection is not sufficient to address this challenge. Non-ambiguous PM specifications are needed. History repeats itself. We find that many classic bug patterns such as null pointer dereference, missing error code still exist in the context of PM, and many similar mistakes are repeated in different subsystems across the kernel. Finally, as also pointed out by other researchers, we believe that research should match reality. That is, for PM bug detection, focusing on one subsystem is not sufficient, and we need to identify methods to handle new bug patterns. We believe that this study is an important step to address the grand challenge. Thank you for listening to our presentation. We have made our dataset accessible to everyone. We hope our study and the dataset could contribute to the development of effective PM bug detectors and the enhancement of robust PM-based systems. I am happy to answer your questions now.
Thanks for the talk, Om. So I think Mickey has a question. I'll actually made him promote him to the panelist so he can actually ask his question directly.
Sure.
Yeah. Thank you for a really interesting talk. You actually answered in your talk one part of my question. So the other question would be, do you have any statistics that you collected about how many of the bugs that you've actually surveyed were found by any kind of automated tool? Were any of them found by any kind of automated tool, like an automated race detection or something like that?
Oh yeah, so that's a good question. Thanks for asking. So we haven't collected any statistics on the bug detection tools used. Rather, we did find some bugs that were detected using kernel address sanitizer like KSAN and other tools. But in regards to data race detectors, we did not see any automated tools that were used. We were trying to actually make K-Race and Razor try to work on this. But as I mentioned, there's one challenge of emulating them on QEMU.
All right, thank you.
Nice. So there's another question from Joel. I have already added him to the panelist. So Joel, please go ahead.
Hi. I was just wondering if you could explain a bit more the term, the misaligned NVDIM namespace. I understand what misaligned means, and I understand what a namespace is. I don't understand how a namespace can be misaligned.
Okay, yeah, so that's a good question. So even we took some time to actually understand these things. So mainly when a namespace is created, it's either set in the DAX device mode or FSDAX mode. And so for this, the way that NVDIM driver handles is by creating a page frame number device, which is another abstract layer on these namespaces. And typically, when the namespaces are created, there is a memory address range created, a memory address range registered to the device, to the system. And if there is any misalignment of the PFN over these namespaces, these issues were actually caused.
I see. Thank you.
Nice. So I have a question. So what is the exact challenge that you see when you're trying to emulate the like the existing NVDIMs for inside the virtual machines? So because I'm one of the authors of both papers that you have talked about, so I'm very interested to know, like, how can you see the challenge there from the NVDIM perspective?
Okay, so firstly, we first investigated Razor. We saw that the authors had made modifications up to the KVM layer of the QEMU, and their QEMU that they used, I think, was not supporting or did not have the support for emulating NVDIM devices yet. So we are trying to actually try to port this to a new QEMU, the Razor to a new QEMU. And that was one major challenge that we were actually facing.
I see. So what, like, will it not work with the LKL kind of environment? Like, what would be the difficulty there?
Oh yeah, so for that, we were looking through the approach of Hydra. We see that LKL currently does not emulate or run NVDIM devices.
I see. Okay. Thanks for the talk, Om.
Yeah,
Thanks for the questions.
Mm-hmm.